Hello, so it's time for me to make a YouTube video of the lecture 8 from PHY 101 Special Relativity. I've done quite a few of these lectures on YouTube before, and so I'm repeating it this year. And as I said last year, I'm not any kind of actor or anything like that, so there'll be awkward silences, mistakes, me fumbling, dropping the pen, people wandering in and asking me things. You have to deal with all of that because I don't have time to do much editing. Okay, so lecture 8 is basically me going through an example, and the example is meant to teach you a conservation of energy and momentum in special relativity. So I'll remind you that the total energy of a particle is given by gamma times its rest mass times c squared, where gamma is the usual 1 over the square root of 1 minus the square of the particle's velocity divided, which equals v over c, in which case I might write that gamma is also equal to the 1 over the square root of 1 minus beta squared. Okay, so that's the total energy. Total energy. And you can also see that if you set v equal to 0, so the particle is at rest, you get the rest energy of the particle, E sub r, is equal to, well, it's still equal to gamma mc squared, but when the particle's at rest, gamma becomes 1, so the rest energy of the particle is just m naught c squared, whatever m naught is, whatever the rest mass is. There's also the momentum of the particle, which is a vector, p in general, and it's equal to gamma times the rest mass times the velocity, and the velocity is also a vector, so that checks out. So if the particle's motion is directed along the x-axis, you get px, the x component of the momentum, equals gamma m vx, or, and the other one's py and pz equals 0, and that will usually be the case for the sorts of problems we will be doing. So let's get started on the problem. So the problem takes place in the centre of mass frame of the two incoming particles. The two incoming particles are an electron and a positron, and they're going to have equal and opposite momenta because we're in the centre of mass frame. So here's my electron, and it's flying in here, and it's got some total energy, we'll call it E minus because it's an electron, and over here we have a positron, and it's coming in with some energy E plus. And this is the x-axis, so both of the particles have motions parallel to the x-axis. Okay? And this particle has some momentum p minus, which we'll just take to be directed along the x-axis, so we won't bother with the vector sign. And this has a momentum p plus. Okay? So if the total momentum, and what happens is these two particles come together and they collide and they fuse and they form Z0. Now Z0 is a heavy particle, and its rest mass, mz, is 90 GeV upon c squared. And of course the rest masses of the electron and positron, the electron rest mass you can write as 0.51 MeV upon c squared. And similarly the rest mass of the positron is the same thing, because particle and its antiparticle have the same masses. Okay, so the question is, how much energy do these two particles have to have in order to make a Z0? What's the minimum energy they can have? Well, the answer you could guess is just half of this rest energy each. The rest energy of the Z is 90 GeV, because it's 90 GeV over c squared times c squared, gives you 90 GeV. If you split that between the two incoming particles, then 45 GeV each will be your guess. And it turns out that guess is actually correct, but instead of just asserting that's the answer and sort of worrying a little bit about why, let's actually go through and figure out why. So for a minute I'm just going to erase the Z that's produced, and let's just consider the incoming particles. So we're in the centre of mass frame. Which implies that the total momentum is 0. Right, so if the total momentum is 0, that must mean that P minus plus P plus equals 0, or P minus equals minus P plus. So you have equal and opposite momenta, equal in magnitude, opposite in sign. So let's figure out what the energies are. So the energy of the electron, E minus, is related to its momentum, P minus, and its rest mass by a thing that we call the energy momentum mass relation. So that E minus squared equals P minus squared C squared plus ME squared C to the fourth. That's the energy momentum mass relation for the electron. Right? What about for the positron? Well, we have E plus squared equals P plus squared C squared plus ME squared C to the fourth. But look, both the particles have the same mass, so the second term on the right is the same in both cases. The first term on the right is also the same in both cases because the square of P minus equals the square of P plus. Sorry, the square of P minus equals the square of minus P plus. If you square this equation, you get P minus squared equals P plus squared, because minus times a minus sign gives you a plus sign. So the first term on the right of these two equations are also the same. So these two terms are the same, these two terms are the same as each other. Therefore, the whole right-hand side is the same for both the electron and the positron, and therefore the square of E plus equals the square of E minus. Now, energies are always positive, and so the only sensible solution of that equation is that E plus equals E minus. In other words, that in the centre of momentum frame, or the centre of mass frame, it's the same thing, these particles have the same energies coming in, and equal and opposite momenta. So if these things are the same, you might as well give them a common name. Let's just call them both E. Right? So now we know that the energies of these incoming particles are both E. And we know that the momenta of the incoming particles are equal and opposite. So let's just call the electron momentum P and the positron momentum minus P. Having figured all that out, we can then figure out what happens when they collide. So they form this Z0, and it must be that this Z0 is at rest, because if it wasn't at rest, momentum wouldn't be 0 in the final state, but we're still in the centric mass frame, so the momentum must be 0. So this particle must be at rest in the centre of mass frame. And because we're in the same frame before and afterwards, we can conserve energy, and well, we've already conserved momentum. The total momentum before was 0, the total momentum after is 0 because the Z0's at rest. Therefore momentum is already conserved. We haven't conserved energy yet, so the total energy before the fusion into the Z0 is 2E, because you've got the energy of the positron and the energy of the electron added together. And the energy afterwards is just the rest energy of the Z0, which is mz c squared. And therefore, solving this equation, the energy of the electron or the energy of the positron, they're the same, has to be equal to mz c squared upon 2, which is our original guess, because mz c squared is 90 GeV, therefore half of that is 45 GeV. Now, let's think about what this means. A 45 GeV electron, right? What is gamma for the rest frame of a 45 GeV electron? In other words, if I was to run along and try and catch up with my electron, and I managed to catch up with it because I was running alongside it, how big would gamma for the frame of rest of that observer who's running along with the electron be with respect to the lab frame? Well, the total energy of the electron equals gamma times its rest energy, right? This is one of the main ways of computing gamma. If you know the total energy of a particle, in some frame, and you know its rest energy or its rest mass, and they're just related by a factor of c squared, which you should of course not calculate by taking 3 times 10 to the 8 squared, you should just algebraically put in the c squared, I keep reminding you of that. Then you can compute gamma for the rest frame of the particle. It's just the ratio of the total energy to mec squared. Now in this case that's 45 GeV divided by 1/2 MeV, 0.51 MeV, which is roughly 0.5 MeV. In other words, that's about 90,000. So gamma is about 90,000 for the rest frame of the electron. Now if you remember, we call particles highly relativistic when gamma is bigger than 7. So 90,000 means that this particle is highly relativistic. So to make a Z0 boson, you need highly relativistic electrons and positrons. We actually knew that already, because if you remember the large electron-positron collider, which used electrons and positrons to make Z0s, that's essentially the main thing it did, produced highly relativistic beams. So we already knew that that was true. Gamma of 90,000 is spectacularly relativistic. So that next part of the problem we're going to do next is to go on and figure out how much energy your electrons in a beam how much energy, a beam of positrons would have to have if they were made in the lab to collide with a stationary electron and produce a Z0. And the way we'll do that is to Lorentz transform from this centre of mass frame into the rest frame of the electrons. And that's what I'll discuss in the next segment.